Welcome you students for the part 2 video on optical measurements. We are going to see about only two parameters again over here. The first two, which is called as refractive index profile measurement, and the second one is the cutoff wavelength measurement. This is the basic block diagram for the measurement of fiber refractive index profile. You can see here the components used are mainly beam splitters, two mirrors. The sample is called as the fiber test cable. Then we have a second beam splitter and we have a microscope to view the fringe patterns. So usually the refractive index is being measured with the help of a fringe patterns which we see through the microscopy. The fringe pattern can occur when two rays are allowed to interfere with the help of a mirror and the beam splitter. So you can see here, first beam splitter, you have first ray, incident ray, and the next one is the reflected ray from the second beam splitter. In this direction you can see after the beam splitter you have mirror, again the beam splitter is the second ray. So whenever two ray gets interference with each other, the interference pattern can occur and the interference pattern can be noted down in a microscope. So one you are going to note down directly, the second one you are going to note down through the sample, which is nothing but your fiber. The difference between these two fringe patterns, you can find out what is the thickness of the slab. And once you know the thickness of the slab X parameter, you can calculate what is the change in the fringe pattern by using that sample. Then you can calculate what is the refractive index profile by using the equation del n is equal to q lambda by X. So refractive index is being measured purely for a graded index fiber. So depending upon your alpha 2, alpha 3, alpha 1, you can find out how your profile index nature gets varied. That is a graph shown here. So it says about we use a interferometer. So that other name for refractive index profile measurement is also called as Mach-Zehnder interferometer method. Interferometer is used to find the refractive index profile, which is capable of studying the interference pattern. One of the interferometer used is Mach-Zehnder for transmission light. For reflection light, we use Michelson interferometer. So interference pattern occurs as a fringe pattern shift Q, which is being observed in the microscope. By noticing down the Q value, and lambda is the wavelength of the optical source emitted, divided by the thickness of the sample kept, you can determine what is N value. That is called the refractive index of the profile. In alternative, so the next parameter to be measured is called as the fiber cutoff wavelength measurement. In this fiber cutoff wavelength measurement, we are going to launch optical signal from a source, and it is allowed to pass into a single turn fiber kept on a table of several length, twisted in form of a coil which has a radius of 140 nanometer. And the output from that fiber is measured through the receiver. So you will have the launching power, you will have the output power. The ratio between the reference signal to the output signal, you can calculate what is your cutoff wavelength measurement. The explanation for this: cutoff wavelength is the shortest wavelength in which fiber behaves as a single mode fiber. In single mode fiber, the normalized frequency value is fixed. VEC is equal to 2.4. Theoretically, we can calculate the cutoff wavelength. But experimentally, if you want to know, we need to find out effective cutoff wavelength. To calculate your effective cutoff wavelength, we should know how many number of modes are present. For single mode, it is fixed. So we are not bothered about single mode fiber here. We are bothered to calculate the cutoff wavelength only for a multi-mode fiber. So mg is equal to pi a by lambda in whole squared into n1 squared minus n2 squared. A is the diameter, L is the optical source wavelength, N1 and N2 are the refractive index of the fiber, core and clad material. From the above equation, you can calculate how many number of modes are present in a multimode fiber. As the number of mode increases, wavelength decreases. Then it is a single mode. As the wavelength keeps on increase, the number of mode decreases. Okay. And the fundamental only one, when the power is distributed, we assume that it is to be under linearly polarized fundamental mode. At that particular calculation, we will get a given cutoff wavelength for a fiber. So you can find out how does the graph occurs for 3 different calculations. So first one is your parameter to be calculated for a wavelength of smaller. As you keep on increasing your wavelength, you can calculate the cutoff wavelength, and the 3 parameters which can be varied over here is attenuation, bend attenuation, relative attenuation and spot size. And the 3 graphs shown will help you to calculate the cutoff wavelength at different points. So the method, theoretical procedure how to do this technique is: first method, the fiber of 2 kilometer length has a single turn coil of radius 140 nanometer. Okay, the light is sent into the fiber and the power PS will be measured for different wavelength. Next, you are going to make another fiber which a bend diameter of 60 nanometer, and you are going to send the same optical power and you are going to measure the output. So as your wavelength is being varied, you already know as wavelength increases, the number of modes should decrease. Initially it is 140, now I am reducing to 60, then automatically your number of modes have to be reduced. The power level reached at 0.1 decibel is the typical power level of the fundamental mode, and this is called the effective calculate wavelength. The second method shown in the diagram uses 2 types of fiber. First single mode, then multi-mode. In both the conditions, the wavelength of the power difference of 0.1 decibel is noted, and the difference of power is 0.1 decibel, then that is going to be the effective cutoff wavelength. So, thank you. So we have calculated in this video about 2 measurement techniques. One is on the interferometer, which helps in calculating refractive index profile. The second one is on the wavelength calculation, which can be purely classified under the multimode fibers. Thank you.